Awesome. Let's do Lagrangian. Yes, this is happening. So the Lagrangian is defined as m over 2 times the metric times xi dot xj dot, where this is, of course, a sum over ij equaling 0, 1, 2, 3. So great. So that means let's first write this all out. So we can 100% talk about where this comes from. This is analogous to 1/2 mr dot squared plus 1/2 m theta dot squared, uh, or I guess it would be I theta dot squared because you need moment of inertia plus 1/2 I phi dot squared. Uh, that's kinetic energy in Newton. We'll review this when we do orbits. I know we're not, I don't know. It's like which video comes first. I wanted to do this one first, but we can do this one next. You can watch this one first. Minus potential energy, um, which is just negative gm over r squared. This is typically called V. Well, sorry, it's actually technically plus potential energy. Oh, sorry, it's minus potential energy, so this becomes a plus. Sorry, right? Because it's the Lagrangian, so it's um, minus this, so it ends up becoming a plus in the equation. Anyway, it doesn't matter. The point is, this is analogous to that. Again, we can talk about where this comes from and what it means later. Let's just practice using the notation for now. I think that's really good. Let's just get the notation down. So when you see this, you think, right, T dot, R dot, theta dot, right, phi dot, right, meaning dt d tau. And again, we want the local speed, not the like global time speed. Dr d tau, because that's more physically meaningful, right? It's not an illusion, right? We want the physical speed locally to measure the Lagrangian, because the Lagrangian figures out like it figures out symmetries and it figures out optimization. So it measures like constraints of like what's allowed by existence, right? So it's this kind of global thing that shows like how a system can evolve or can exist or not, right? It really is this like window into, yeah, constraint is the word, right? So you want to think of like kinetic energy is what's trying to happen, and potential energy is forces is what's limiting it from happening. And so the difference between the two is a measure of the constraint. Does that kind of make sense? I don't know. Either way, that's the idea. Let's just practice using this though. Cool. So L would be m over 2, and there's your 1/2 m and your 1/2 mv squared, right? Times, again, so this would be gtt t dot squared, because only when I equals j, when I does not equal j, everything equals 0, because there are no diagonal terms in the matrix, right? In the metric. Right? So GTT works. So that means xi is x0, xj is x0. So this is I equals j equals 0, right? Is t plus grr, r dot squared plus g theta 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 dot squared plus g phi 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 dot squared. Cool. So this is kind of like that. Now you might say, where's the potential energy? The potential energy is written in the metric. Bum, bum, bum. That's like the point. You might say, where's the minus sign? Don't worry about it. It serves the same purpose. This is still the constraint. And again, we can go over that later. I don't know if I want to make a video about that. Right? Cool. So here's the whole point. This GTT, right? Let's write this whole thing out. GTT is c squared 1 minus rs over r. That depends on r only. T dot squared, right? Plus r dot squared over 1 minus rs over r. Again, only a dependence on r. So right away we see dl, that'll be a partial derivative, but I don't really care about partial. It doesn't matter, same thing, right? So dl over dr is not zero, right? It depends on r. It's not invariant. There is no symmetry with r. So the word symmetry, the word invariant are the ones we want to use. So this is not invariant with R. It varies with R. If R changes, it changes. That means there's no symmetry, which means if I change R, it's not the same. Symmetry is like if I change something, it's the same, right? Symmetry is like if I rotate something, it's the same. Cool, it's the same. That's a symmetry, right? So it's a redundancy, right? So this is not redundant, right? Meaning if I change R, it's not the same. So cool. That's just informed. So let's keep going. Plus g theta theta is R squared, theta dot squared. Again, not invariant with R. But here's the last one. It's not invariant with theta either. Because, right, we have the theta here. So it's not no symmetry R or theta. But what doesn't it have? It doesn't have T and it doesn't have phi. Wow. So what does that mean? It means that there's constants. It means that there's symmetries. So time symmetry. This is Noether's theorem. Noether's theorem and the Lagrangian go hand in hand by the Euler-Lagrange equation, which is d d tau times, and by the way, we can talk about uh, why this is tau. And the point is it's physically meaningful and it's locally representable, right? It's not an illusion, right? Is actually the reason why. It's like locally the most real thing is the reason why this has to do with the Lagrangian and symmetries. dl dxi dot equals dl dxi. So if dl dxi, and by the way, we can derive this later, or I can derive this again, maybe with you or in a separate video, I can try. But the point is conceptually, if L is invariant with xi, meaning x0, time, this is either time or r or theta or phi, right? If that's zero, then this is constant. Which means that, sorry, not this, but then this is constant because d tau of it is zero. So for instance, right, dl dt, that's partial, is zero. So d tau of dl dt dot is zero, which means dl dt dot is constant. We call this PT, the time momentum. The word momentum has to do with a constant in Noether's theorem. Be careful, that's not the classical momentum, right? There's a global use of the word momentum to mean that which is constant due to a symmetry, which I know is confusing, but the point is this is now meta. We're now going into, okay, there are constants in the universe due to symmetries. Due to the fact that this invariant in time, we get a measure of this constraint of what's allowed, gives us this conserved quantity which never changes. So we call this energy. This is the origin of energy. Uh, It turns out we want to write it as energy per mass, and we can talk about that later. That's a subtle, surprisingly subtle. I know it's seems like it's important and it is, but it's subtle. It ends up, the point is we want, the reason we write it as energy per mass is because we want mass invariance as well, because we observe mass invariance, right? Gravity affects all masses equally. That's an invariance. But that doesn't end up in its, that's not in the Lagrangian. That's mass isn't a cause, right? Um, in terms of like it's not a variable in terms of the mass feeling it, right? The mass feeling something, the feeler mass, not the like source mass. The feeler mass is doesn't matter. Obviously, the mass of a black hole will affect it, so that's not an invariance. But the feeler mass is invariant, so that's why we include it in here. That's hand wavy, but good enough for now. The point is, this is where energy comes from. So what is dt prime? Pause the video and you do it yourself. Go back, take the derivative of this. What do you get? All right, on pause, you should get that this is, in general, right? Uh, m times gtt times t dot, right? Which is m times 1 minus rs over r times t dot times c squared. We define that as E. So we put the M over here. And so we get E over M. I like E over MC squared equals 1 minus RS over R times T dot. How it's typically written is this. E, where E is E over M, this is the standard physics thing, is C squared 1 minus RS over R T dot. This is how you're typically going to see it. I like this one better, though. Or that E equals MC squared 1 minus RS over R T dot. What's cool is that T dot is gamma. So this reduces to gamma MC squared at R equals infinity. This is the special relativity uh, mass energy plus kinetic energy, not including space-time curvature. This is so cool. I think it's so cool. I think it's just crazy, right? So it's all of it woven in one. So you can look at this as E equals gamma MC squared times the Schwarzschild curvature. We're going to write it like this because then we can plug it back into the metric, which you can look at the next video to do that, and you can solve for equations of motion. You can actually reproduce Einstein's gravity. Sorry, you can reproduce Newtonian gravity from that. You can solve for the gravitational acceleration, which I think is pretty amazing. The next one we can do is, you know, the theta dependence, sorry, the phi dependence, right? That's invariant. So we get P phi is defined as dl d phi. You go ahead and derive that now. Pause. Unpause. You should get that's mg phi phi times phi dot. See if you can figure that out from looking at the equation, which equals m r squared sine theta squared, sorry, sine squared theta phi dot. So we define that as the angular momentum. This is where angular momentum comes from. It comes from rotational symmetry. That if you rotate your black hole or you rotate your reference frame around a black hole or the Earth, rotational, that's what that says. That's an S, believe it or not. Rotational symmetry. There we go. We got it. How are we doing? Is this making more than 0 cents? Isn't this so cool? This is Noether's theorem applied to angles. We get angular momentum from this. Careful, this is capital L, different from the curly Q cursive L, which is the Lagrangian. So we get L over M, once again, is R, sorry, I think there's a negative sign there. Yeah, there's a negative sign there. Negative R squared sine squared theta phi dot. Boom. When we do Newtonian gravity, if you set theta equal pi over 2, you should get that the angular momentum is mr squared theta dot, where there's no negative. The negative isn't actually, no, it is or it isn't. I can't remember. We'll just say it is for now. Um, and this is the same as Newtonian. And when we do orbits, this will make 1,000% sense. But let's just look at a conserved quantity in terms of the Lagrangian. In terms of Noether's theorem, we have a symmetry. We get this conserved quantity. It turns out it's going to match what Newton modeled perfectly. That's all we need for now. Where these conserved quantities come from, see if you can let it make sense, but it has to do with, and notice how these are the fundamental principles, right? Invariance, right? Symmetry, constraint, right? The universe works on form being constrained. It works on invariances producing predictable quantities as outcomes, as like bookkeepers. So energy doesn't have any physical meaning besides that which represents time symmetry. Cool. I'll let that be. Let that sit. I hope the math made sense and that the notation made sense. Kind of more than anything. I'm tempted to go more, but I think that's perfect, especially the Einstein notation and the sum notation and then taking the derivative of that. Cool. Yes.